All right, hey guys. This is another announcement about the mentorship program. Our apps are still open and they're due by October 1st, and that's around next Friday. It'll be a great way to learn and make friends and just have your mentor-mentee pairs. Anyone can apply if you are an alumni, if you know someone who's an alumni who wants to participate, if you're an upperclassman, lowerclassman, anything of the sort. We have the link here and the QR code just for your convenience. Thank you.
Okay, so we pull up chat on here.
I got a quick announcement.
All right, we got another quick announcement.
Sorry, boss. Can they hear me without the mic?
Yeah, that's your Zoom mic. That's
right. Oh,
if
cool.
Someone on Zoom can confirm if they can hear it, that would be good.
Awesome. Cool, guys. All right, so this Sunday, there's going to be an event hosted by ACM. It's at Plaza of the Americas. It's from 1 to 3. There's going to be pizza, and I heard there might be some Publix popcorn chicken too. There's other clubs there like Wixie, DSC, us, and SSD. It's going to be a massive networking event where you meet the other clubs, meet the other people there, and kind of just meet new CS students and potentially see if you have any other interest in other clubs too. So come out, show face, network, eat some good food, talk to new people. And I'm going to be posting an interest form or an interest poll tonight or tomorrow on Discord. So please react to it, whether you're coming or not, just so I can see a total head count so we can get enough food for the event. Sound good?
You want to do pizza or? I forget when normally.
You have another shots.
Oh, do you want to present font size?
I can do shots.
Oh. Yeah. Okay. You want to go ahead and.
We have more gloves.
One more announcement before we start the actual presentation. We're having a resume review on October 6th, hosted by Raymond James. And so this is a good opportunity to network, get your resume reviewed. It will be after many of the major career events here, but you can still sort of go over some things you want to change, or if you're still applying, this will be very useful. And also for our own upcoming security career fair, this will be a great moment to review that, you've got everything in order and then it looks good for a recruiter. So I'll be posting a form link to upload your resume for both the resume review and the security career fair. You can choose if you want to have it collected for both or just specifically a single event. Thank you.
Okay. So I'm going to go ahead and get started. Today is going to be Intro to Reverse Engineering. So I guess I'll start with a brief preface of why we need reverse engineering. So every single day when you use your computer, you use some kind of software. You might use a web browser to go on Canvas, stuff like Google Chrome or Safari, might write your papers in Microsoft Word or Pages, and you have a computer that likely runs any of those operating systems. But the thing is when all the software on your computer is usually distributed to you as, it's either A, the software is closed source, and B, it's usually distributed as just a binary. So you only have access to the compiled program, which makes the software effectively a black box. You can't really tell what it's doing. You have no way of looking at the code to see what it's doing. So that opens up a lot of possibilities. Maybe the software is malware or ransomware that will encrypt all your files. Maybe it has a backdoor in it. Might have a critical vulnerability that a skilled actor could exploit. Or I guess if you're super unlucky, maybe it has all of those. So the question is, how can we find out, right? Because if you look at a program on your computer, you double click Microsoft Word, you have no way of knowing just by looking at the icon that that's a safe program to run. And antivirus doesn't always work, and you have no way of knowing what you're about to run. So fortunately, and as you might guess from the title of the presentation, we can reverse engineer to find out more about what the program does. So reverse engineering is pretty simply just software analysis without source code. So you don't have source for most of these programs, odds are, and you need a way to be able to still find out what they're doing. So we use special tools to do this, which I will cover momentarily. And your goal is just to discover how this piece of software works. So you might want to take a look and find out what it's actually doing under the hood, or if it's going to do anything bad, or if it's susceptible to do anything bad. But why would you want to do this? One example is for security. So oftentimes you might want to verify that software is safe. This comes back to the first example where you don't know if something you're about to run on your computer might actually be malware. You can reverse engineer and find out more about the software and see if it's potentially doing malicious things. You also might want to discover a vulnerability in that software, which you can exploit. So lots of software has exploitable vulnerabilities that can lead to code execution and all sorts of nasty stuff. And to discover these, you will need to reverse engineer. You might want to do this for fun. So if you ever played a video game that has mods, or you've ever used cheats for video games, that likely required somebody to reverse engineer how the game works so they could create those cheats or mods. So if you're interested in doing either of those things, reverse engineering is a valuable skill in your tool set. Also, maybe for profit, maybe you want to replicate some sort of proprietary algorithm or create a ripoff of other software. That has pretty large legal implications, so maybe don't start there, but you might want to do that. And pretty commonly, or the way that you have most likely experienced reverse engineering firsthand is the bypass of software copy protection. I'm not accusing anyone of anything, but if you've ever downloaded any software that has been cracked or you did not pay for, you have profited off of somebody's reverse engineering. So I assume that most of you are computer science students, maybe by a show of hands. Okay, so most of you computer science students. If you're familiar with C or C++ or any other low-level language, that's a good starting point. Especially, you should feel comfortable working with pointers because that comes up a lot. And having an understanding of computer fundamentals, like knowing what a processor is, knowing how RAM and memory works, that's important. If you already have familiarity with stuff like instruction set architectures, which if you're in computer organization or have taken computer organization, that probably sounds somewhat familiar to you, especially assembly language as well. If you've taken computer organization, you're probably familiar with that to an extent. And other low-level concepts like the stack and the heap are good to know, but you will eventually learn all of these with time should you decide to pursue reverse engineering. So I guess my quick disclaimer is that this is a very introductory talk. Did anyone see me give this talk in the spring by any chance? All right, good. Not a lot of people, because that one wasn't as good. But this is an introductory talk. I'm not going to go into the nitty gritty of x86 assembly or anything like that. An hour just isn't enough time to kind of teach all the basics. So also, reverse engineering is pretty challenging. It requires a lot of practice to get good at. Just don't be discouraged. If you think this sounds interesting, spend some time trying to learn it and give it your all. And eventually, you can learn what you need to learn. And also, as I go through, if you have any questions, I don't mind if you just raise your hand and ask. Like, I don't mind answering questions mid-slide. So either Zoom or anyone here, feel free to raise your hand or ask questions as we go. So either in the Zoom chat or I guess show of fingers, how familiar are you guys with reverse engineering? And I can maybe pace myself differently depending on the case. So 1 would be that you're completely new, and 5 is you should be teaching this, not me. 2s, 1s, 3s. All right, so we got a lot of new people, which is good. And 1 in the Zoom as well. So all right, you guys are the target audience of this talk, so that's good.
I got a question.
You have a question?
Does it help with reverse engineering if I'm a human assembler?
Yes, it does. For people on Zoom, Scott was heckling me. That wasn't a serious question. You didn't miss anything. So I guess to start with reverse engineering, we will cover forward engineering, which is a lame joke. But so developers, which might be you guys, you've all, most of you I imagine have taken some sort of programming class. Developers write source code for software. The compiler, parses that source code, emits assembly, The assembler assembles that into machine code. These get linked. That's not all that important. But the long story short is that you write code and it turns into an executable. And it goes through a lot of steps. And you end up with this executable, which is just a big bundle of machine code that your processor understands that doesn't look anything like the source code you wrote. And as a consumer, that's what you receive most of the time. This won't turn into like a free software rant, but that's usually what you get on your computer. You get the compiled executable, it's what you download, and that's all you have. Machine code only really vaguely resembles source code. So variable names, structures, comments, all that kind of stuff is lost. So when I talk about not knowing what code does or what a program on your computer might do, all that kind of information is not present in the copy that you get. Only the developers have that. If you're lucky, you'll get function names and maybe strings, but not always. So here's a really brief example. You don't have to understand what this means, or you should at least understand the top part. That should look familiar to you as a main function in C. It's just a main function. All it does is return 0. So if you compile this to Intel x86, you get those lines of assembly at the bottom. And that first line is kind of just optional. That's for your benefit. So that function compiles into 2 instructions, just an XOR EAX, and return. And if you don't know what that means right now, don't worry too much about the specifics. All that does is it sets EAX equal to 0, which is the return register, and then it returns. So that's pretty close to what we saw in the source code above. A little more complicated example is this function here. So you should recognize this, or the C should be easy enough to read. All it does is just goes through an array of integers and it sums them all up and returns that value. That compiles into this assembly, which is a little more scary looking. Once again, this is something you'll have to learn a little bit yourself. I can go over it towards the end and do a kind of crash course a bit if we have time. The main thing I'm trying to iterate here is you should notice that the assembly does not look an awful lot like the source code, and there are not really names of variables, names of arguments. Most of you right now looking at that would not recognize that as the top function above. So the big picture, the idea that I'm trying to convey is that the compilation process is very destructive. So even though you get a program that you can run on your computer and something like Zoom or Microsoft Word, all those run just fine, but the code that runs in your computer, which is compiled instructions, looks nothing like what the developers originally wrote. And that's what I'm trying to convey, is that it bears little resemblance. Almost all semantic information, like variable names, function names, comments, obviously, are all lost. So this makes analyzing that code rather difficult. It's like trying to sift through something with very few clues. Fortunately, difficult does not mean impossible. So we can use special tools to analyze programs on our computer, and with some practice and building up some knowledge, we can make sense of what we see. This is effectively reverse engineering. So I'll start with our kind of tools of the trade. Disassemblers is a category of tools that you will spend a lot of time using. So these are often going to be your primary tool for reverse engineering. They will take a program on your computer. You can drop a program, like I'll keep using Microsoft Word as an example. You can throw your Microsoft Word in there, or throw a challenge from a CTF, or throw any program in there, and they will parse that executable and turn it back into readable assembly. And I put readable in quotes because readable is subjective. It will look pretty scary at first until you have spent more time reverse engineering. These will also help you visualize control flow and stuff like basic blocks. So they'll help you out a little bit. They'll try to make the intent of the program a little more clear. They're pretty smart tools, so they do more than just disassemble. But a lot of them will often include a decompiler, which attempts to translate assembly back into a form of pseudocode. which is there to help you as the reverse engineer. I'm going to be pedantic about this and say that decompiler is kind of a misnomer because you can't recover the original source code for compiled programs on your computer. So all the decompilers out there, that's commonly what they're marketed as, attempt to make educated guesses. They look at the assembly and say, okay, well, what might this look like if this were C code? So some of the popular disassemblers that you will see, the first and foremost is IDA Pro. This is the oldest and most popular disassembler. IDA Pro is older than I am. It came out in 1991. So they've had quite a bit of time to make their product. They have arguably the best pseudocode generation out of all the disassemblers. So if you think that you're going to rely on that a lot, IDA Pro is probably a good choice for you. It is very expensive if you want to use it for commercial purposes. They have a trial which you can download, but that's IDA Pro. Binary Ninja is a newer, more modern reverse engineering platform. So Binary Ninja's only been around since 2015. Publicly, it started a little before that as an internal tool. And Binary Ninja tries to do things in a more modern way. So it analyzes using intermediate languages, which I won't get into right now. But it has a good API, IO-based analysis. It's a really interesting tool. And that one you can get for $75, which is your student discount. Ghidra is an internal NSA tool that originated in the early 2000s, and they made it free and open source in 2019. So definitely not a bad tool to start with. I think, I don't know if Zoom can see my shirt. I clearly have a preference. I'm wearing a Binary Ninja t-shirt, but any of these are good places to start with for just getting started out. Our next kind of main category of tools are debuggers. So debuggers let you analyze software as it runs. So disassemblers is when you disassemble, it's what's called static analysis, where you load the binary in there and you disassemble and you analyze, but nothing is running. You're kind of just looking at assembly instructions and seeing what you think is going on. Debuggers let you kind of hijack a program and step through it one instruction at a time and really see what's going on. And you get to do a lot of fun stuff with debuggers. You can, change values in memory as the program runs. So you can change the value of a, for lack of a better term, variable to something else. You can override control flow, tell the program where you want to go instead of the program telling you where it wants to go. And you can set breakpoints and do all sorts of stuff. So debuggers are a good way to get an idea of what a program is doing kind of live and step through and really just watch everything play by play. Some of the popular debuggers are GDB. This is the standard debugger on Linux. There's lots of great third-party, I meant to write add-ons, but I got adding. That's a typo. Anyways, lots of great third-party add-ons for GDB. There's also LLDB, which is very similar to GDB, excuse me. And that's the debugger that's made by the LLVM project. It is less popular. There are not as many cool add-ons, unfortunately, but it is the standard debugger for macOS and iOS. So any of the Apple platforms, if you're interested in doing work on those, that's your standard debugger. And then WinDebug, which is, or WinBag, depending on who you ask, but that's Microsoft's official debugger for Windows. They make it, and it's the only debugger in Windows that can debug the kernel, which if you're new to reverse engineering, probably won't be where you start, but for what it's worth, it's the only one that can do that. It's not a bad one to learn. Another tool that I decided to put on here is hex editors. If you're not familiar with a hex editor, it lets you view a file as plain bytes. So you can open all sorts of file formats. Maybe if you're reverse engineering a game, you can open up some of the assets for the game and look at them. They're great for, and like I said, great for analyzing binary file formats. If you are trying to patch programs, you can also use a hex editor for that as well. Some popular hex editors are 010 editor, which is kind of like a hex editor on steroids. It's cross-platform. It's got a lot of advanced, crazy features. It is paid, so it's $50 for home or academic use. HXD and HexFiend are great options for Windows or Mac respectively, and those are free. But those will just be your basic hex editor functionality. And for what it's worth, Binary Ninja is also a hex editor as well. If you like using that as your disassembler, you can use it as a hex editor. If you haven't used Python before, or if you do know Python, I guess you're in luck. It's great for doing quick tasks while reverse engineering. You might have to do some odd stuff like, XOR a ton of bytes together or write a script to do something. Python's a quick and easy language, and it just comes in handy. And a lot of the other third-party tooling for reverse engineering is written in Python, and a lot of the reverse engineering tools have Python APIs. So it's a good programming language to learn. So I guess I'll ask if anyone have any questions first, anything I say that was confusing or you would like to know more about, because then I will go into doing some basic demos and then I can kind of cover stuff as people would like, because we still have plenty of time. All right, so we are all perfectly clear. So I'll go over some basic demos. This is Binary Ninja, which this is my preferred disassembler. So I'll be going through in here. But the first thing I'll do is I will pull up okay. So this is a little program I wrote. Is everyone able to see that clearly? Should I make the font larger? How about now? Better? And I will quickly that should be sufficient. So this is a little program I wrote, and I will walk through using this program. So you'll see if I just try to run it, the first thing it spits out is error, a username and password are required, and tells me that I should supply them both as arguments. So we'll go ahead and we'll try a username and passwords. I'll try UFSit, and I'll try 1, 2, 3, 4, 5, 6, 7 is the password. That says authorization failed, please try again. So maybe I'll try a different one, maybe UFS and ABC, and it's saying the username and password must be exactly 6 characters. So UFSit, 1, 2, 3, 4, 5, 6. Whoopsies. So it's still saying authorization failed. So I'm not going to sit here and try all day to find out what exactly the password is, because that would be a huge waste of time. Fortunately, we can start reverse engineering a bit. So let me close some of this stuff on the side here just so we can see a little better. So I'm going to bump the font size down just a little. I can fit a little more on the page. So this is the disassembly of the program that I just ran. Once again, if this looks scary to you, that's probably normal. But with time and learning a little bit, this should start to make a little bit of sense. But even with ignoring the contents of all of these blocks here, we should be able to deduce a little bit about what's going on. We can see with these arrows that there are decisions being made, and we're going one of two places depending on what the decision is. So if we look up here, we can see that there's a decision being made, and then we're either going to go to this function, show usage and quit, or we're going to keep doing stuff here. So if you recall from when we ran with a program with no arguments, we got this usage message. So that sounds kind of like what's going on here. It's checking if we did something correctly, and then if we didn't, we're going to show usage and quit. If we double click here, we can actually see these strings that we referenced earlier. So this is the same message that we saw here. Fortunately, this is already named show usage and quit, but if it wasn't, you could look at those strings and figure out what it does. So then we come down another branch here, and I'm trying to actually ignore the specific content of what these blocks say, and I'm kind of trying to illustrate that we can look at just the control flow and see kind of what's going on. So we can see that we come down here and make another comparison, and we're either going to show the length error and quit, or we're going to keep doing more stuff and get to this check credentials part. So this sounds like the part that we were doing earlier to check the length of the input. We come down here, we do check credentials, and then we either go to show auth error and quit or show success message. But thankfully, we have function names that we can kind of use to our advantage. So this is the disassembly. This might look a little familiar from earlier. Like I said, most tools include some sort of decompiler or pseudocode generator. So I'm going to switch this over to high-level IL, which is the decompiler in Binary Ninja. And now this looks a little more like C, maybe. This should hopefully look a little more familiar to you guys. So if arg1 is less than or equal to 2, that sounds kind of like if you're checking what argc is in main, if you're familiar with C programming. Then from there, we're calling strlen twice, which if you're not familiar with C, just tells you the length of the string. We're putting that result into this variable, rax3, and checking if it's equal to hex C, which is 12, or 30. The display is an integer if you can't convert in your head. And then we're going to make another decision, show length and quit, or check credentials. If the result of check credentials is equal to 0, we're going to show our auth error. Otherwise, we're going to show our success message. So you don't have to fully be literate in assembly language. I would assume that just by looking at this part might be confusing. But if I tell Binary Ninja that this is actually a character array, now we can see this is indexing this array properly and asking for the first and second, or the second and third element. So I guess I'm trying to illustrate that you should be able to see this and kind of, even without knowing the specifics of assembly, maybe this looks a little bit more like code to you and it's a little more understandable. So I guess I will walk through how I might try to solve this challenge. I did write it, so that makes it easier. But I will, we're going to peek at this check credentials function now. And I'm trying to move the Zoom screen share UI out of the way. So this is our check credentials function, and it takes 2 strings as arguments. So once again, this is high-level IL. If you prefer to read it more like code like this, you can also read it like that. So I think this makes it a little bit easier in this instance. But what we're doing is we're going through here and we are taking this first argument and we're going through and we're just XORing each of the characters in this string with the value hex 47. And you can either see that, you can see this kind of loop here in assembly. Like I said, though, you can just come into high-level IL and see it like this, and it looks a little more like code. So we know that we're going through here and we're XORing the input with a certain value. And then we have this call if, if strings match is equal to 0, then we return. And then we have another call to if strings match equals 0 and we return. So, and we're doing this same thing down here again, where we're going through all of the characters in arg2 and we're XORing them with 47. So this is using some sort of routine where it's going through and XORing the strings and then comparing them with a known value. This is kind of a, attempt at obfuscation, right? If we look at strings match, it just calls string compare. I think this is one of the things that I was talking about earlier. So these tools aren't perfect. So I think that Binary Ninja actually is missing interpreting that function has arguments. So if I add that in, which I happen to know, and if you looked at the assembly, it would have been more clear, but I'm trying to steer away from that for now. This strings match function actually has arguments. So now if we look at what we're doing, we're going through, we're doing our XORing, and then we're checking if this new XORed string matches this. And then we're doing the same thing with the second argument. So we're just checking two pairs of things. I'll rename this to username. And password. And that might be a little more clear. So how do we solve this? I will choose to break out Python because that is what I talked about earlier. And I will embarrass myself because I don't use Python a lot and I'm probably going to forget how to do this. So we're checking against these two strings here, this percentage 523, and then this weird looking one. If you guys are familiar with how XOR works, XOR is exclusive OR operation. So A XOR B, I forgot what the actual like kind of math definition of it is, but if you XOR something with a value and then it's XOR it back with the value, you get back what you got originally. So I will write some brief Python, encrypted, and so we'll put our encrypted username in there, which I will just copy out of there. And then I'll copy this out as well. Okay. And then we're just going to loop through each of these strings. Does anyone remember how to do this in Python? Or C in encrypted. I don't need an index. I think this works. What's up? Can you XOR characters? You have to do the board and char thing first. No, you can. Dang. If you don't understand the specifics of this, that's okay. Okay. So we just tried that on the username, and it looks like when we print this encrypted username XOR with 47, we get Brutus, one character at a time. So that's probably our username. We'll do the same thing for the password here. And Brutus and Alpine look to be our username and password. So we'll try that. 6. And boom, now we got a different message. Authorization successful, error, this program does nothing. So if I open up the source code for this, you can see that this is what we had in here. We had our XOR key is 47, hidden username is this and this. And if we look, I'll show you the source side by side with the program. And you can see this looks kind of similar. So we check if argc, our first argument to main, is less than 3, which is the same thing as less than or equals 2. If that is true, then we show usage and quit. We set up some variables for our arguments, which we're doing here. We call strlen and add them together and then check if they're equal to this credential length, which is 6, we check here. So you can see these look kind of similar. And thankfully, Binary Ninja is able to kind of make that a little more clear with the high-level IL. This is the assembly for it. So you can see that looks a little less similar. So we solved the challenge successfully. So from here, I have a couple more challenges I can do, but I'll wait to do those towards the end. I will cover a couple more things. If anyone has questions, now would be a good time, either if you're on Zoom or in person, just raise your hand. I guess, what are your next steps? I know that was probably, if you're completely new to reverse engineering, that was probably a confusing and not very good demo. Like I said, it's kind of hard to teach reverse engineering in an hour because it's just a lot of content. And I don't want to sit here and explain. What's up?
I got a legit Ninja question. So don't dismiss
All right.
me, guys.
What's up?
How does Binary Ninja handle
Dwarf info? The question was, how does Binary Ninja handle dwarf info in a binary? I believe there's a plugin for that.
Okay, so it's not out of the box.
No, it's an official Vector 35 plugin.
Okay.
But
Now, does it work on Dev or no?
yeah, why wouldn't it?
I don't know. Peter did some API stuff.
Anyways, if you don't know what dwarf info is, don't worry about it. So your next step, like I said, last semester, I kind of gave just an hour-long talk about a bunch of different x86 instructions, which is not enjoyable. So your next steps, I would say download a disassembler and a debugger, and I can go give a little demo of a debugger afterwards, but download a disassembler and or debugger, and just try throwing some stuff in there. I'm sure Scott has plenty of CTF challenge binaries he can point at you. If you're, Scott, you still at your computer?
Why you want to?
Can you upload the things I sent you?
Oh, okay.
Scott, I sent Scott a handful of reverse engineering challenges, including the one that I did right now. That one, all of them are compiled for Linux. So if you have a VM or Windows subsystem for Linux, you'll have to run them in there. I have the source code for all of them, so I'll compile them for other operating systems upon request later. So I would download, excuse me, I would download a disassembler and debugger of your choice. And then from there, there's kind of a lot of material that you'll have to learn. So there's getting familiar with the x86 architecture. Unless any of you in here have one of the brand new MacBook Pros or MacBooks with the M1 chips, I will bet my kidneys that you have a computer that runs x86. So that is the most popular processor architecture, and that's what the code on your computer will be compiled as. So that would be a good one to learn so that you can reverse engineer stuff on your computer. Once again, if you're in computer organization, hopefully you've learned a little bit about the stack frames, maybe dynamic memory. I'm in computer organization currently, so I don't know how much that covers. But stack frames, dynamic memory, those are all kind of low-level programming primitives that are important to understand. There's also calling conventions, which when you write code, and you call a function and you pass it arguments, it's that simple in your code, basically. But when you get down to the nitty-gritty of how processors work, processors have registers, there's a stack. How do you pass arguments around? There's all sorts of what's called calling conventions, which define how you pass information around between procedures in assembly. I would recommend that you try some practice challenges. Like I said, I think Scott will put the ones that I sent to him earlier in the Discord. If not, I'll put them in there later. Lots of CTFs, if you've been playing CTFs with us, have reverse engineering challenges. And there are plenty of good, what's called CrackMe challenges on crackmes.one, which is a website you can go to. It has all sorts of, beginner to advanced challenges. And those ones will be similar to the one that I just showed you, where you have to maybe find what the password is or reverse a license key algorithm or something like that. As far as recommended resources go, there's a great book which I would highly recommend. So if this was interesting to you and you decide like, hey, I want to know everything about this and really understand, the Reverse Engineering for Beginners book is very good. It's like 1,400 pages. So not a afternoon read, but it has a lot of content in there, and that will cover almost everything you need to know to become, proficient at basic to intermediate reverse engineering. One website, which I will show off in a moment, Compiler Explorer, is an incredible website. So if you're learning assembly, right? Once again, if you've taken programming, you took C++ or C, if you're writing code in C++ or C, that gets compiled into assembly and then machine code on your computer. I found it very helpful when learning how to read assembly to see how certain programs compile into assembly. So as a reverse engineer, it's your job to look at the assembly and work backwards, but I think that it's very helpful to work forwards first and see the patterns and idioms and then work back from there. The NSA has a page on reverse engineering resources, which I forgot to link here, but I do believe it's on our website, ufsit.club. If you're not familiar with Live Overflow on YouTube, great channel, all stuff related to cybersecurity, and he has a number of videos on reverse engineering as well, and even binary exploitation as well, if you're interested in that. So if you're interested in binary exploitation, any kind of exploit development, binary exploitation, stuff like that, that goes very hand in hand with reverse engineering. So reverse engineering is a skill set you'll need to develop if you plan to do that. Lastly, the UFSIT Discord server is a great place to ask questions. So like I said, this talk is hard to fit into an hour if I want to give examples of everything. But if this sounds interesting to you at all, which I would hope that it does, feel free to ask in the Discord server or after this, and I can help point you in the right direction and help you out. A year ago now, I joined the Discord server and I had questions about reverse engineering and I asked, and there were a lot of helpful people who were able to point me in the right direction. So I would highly recommend that. Does anybody have any questions of any kind? This is the end of the slides. I'll go into a little more demos afterwards, but if everyone has general questions, specific questions, off-topic questions, I can answer those.
Your affiliation with Binary Ninja?
I am technically an employee there. No, I interned at Vector 35, which is the company that develops Binary Ninja, over the summer. And that turned into kind of a part-time thing. So I'm still working there part-time now. So I have a little bit of a bias, which is why I saved some of my more disrespectful Ghidra comments for another time. But Scott.
John, what's your favorite Z80 instruction?
I don't know that instruction set. The question was, what was my favorite Z80 instruction, which is another heckling question from Scott. But
what architecture are you using for computer organization?
So the question was, what architecture are we doing in computer organization? It's ARM this semester, which I have an M1 MacBook now, so that's my architecture. So that's like not a problem. But if ARM is the architecture that's in all your phones and stuff, I won't. Cheryl's already told you all of that. I won't go into the details. If there are no other questions, I will go ahead and show how much time we have. We have another 10 minutes. So I can either do some more reverse engineering challenges, which probably won't be super exciting to watch. I can show Compiler Explorer, which I think is a really cool website. Question. What, Compiler Explorer? Okay. Compiler Explorer is one of my favorite websites of all time. It is godbolt.org. And I'm not affiliated with this website. So unfortunately not. But Compiler Explorer is a great website. So what this does, like I said, you as a developer write source code, it gets compiled into assembly and machine code, and then that's what runs on your computer. This lets you visualize that process on a tiny scale. So for example, this is a C++ function on the right, and you can choose insane number of languages on here too. So it's not just C and C++. If you like Go or Java or OCaml, or if you're really cultured and you like Pascal, you can use any of these on here. And the cool thing is you can kind of highlight each of these lines and it will show you the assembly that these lines translated into. So the examples that I gave earlier actually were spat out of here. So this is a function that just squares a number, right? I don't know if this font is large enough. This is a function that squares a number. It takes in the number as an argument. Excuse me. Roberto says, thank you for the presentation. You're welcome, Roberto. And then it returns just the number times itself. So if I highlight over here, we can see that at this function declaration, it's producing these 3 lines of assembly: push RBP, move RBP RSP, and then move into the address point to 2 by RBP -4, whatever is in EDI. So if you've been reverse engineering for a while, you will recognize this as a function prologue, or at least the first 2 arguments. And then this line here is taking the argument and moving it into the stack for the current stack frame, which is a little out of scope for this topic in this presentation. And then we're moving into EAX, which is just a processor register on x86. We're moving the value, or more specifically, the double word pointed to by RBP -4, which is going to be a memory address. So we're just loading a value into a register. Like I said, if you're in computer organization, if you're familiar with ARM assembly, if they're teaching that computer organization, x86 isn't that much different. Some of the instructions are even almost identical. As far as the mnemonics, it's a pretty different instruction set, so I take that back. But once you learn one assembly language, learning another is usually a little bit easier. And so we'll see here, we're moving that value into EAX and then multiplying EAX by itself, pop RBP in return. If you've been reverse engineering for a while, you'll just know as a function epilogue, and then that's it. Now we just return the function times or the number times itself. But this website, I would very highly recommend, because assembly is tricky to learn. And the other thing is that handwritten assembly looks a lot different. I'm trying to find, there we go. I'm trying to find that code that I put earlier. So handwritten assembly looks a lot different than compiler generated assembly as well. So compilers do all sorts of nasty tricks and optimization and weird things, which when you're learning to reverse engineer is something you'll need to learn as well. So compilers obviously want to make fast performant code. So sometimes I wonder if I can get it to do it here. Like I'll comment all this out. I'll see if I can give an example. Okay, so here's an example. So everyone probably recognizes that is just return the input divided by 7, right? There is a divide instruction in the x86 instruction set. You'll notice that it's not here. It is move with sign extend and then multiplying by this crazy number and then shifting right by 32 bits and doing all sorts of crazy stuff. This is an example of a compiler trying to be smart. So division can be expensive and the compiler just goes, oh, I know that instead of dividing by 7, I can do all this cursed arithmetic and it produces the same output, but it's faster. So that's something you'll kind of have to learn a little bit as well. So when you see crazy stuff like this. Sometimes it's just as simple as doing, like arithmetic or division or some sort of optimized math procedure. And you're probably familiar with, this is slightly different, but this is a famous function, the fast inverse square root. Oh, I don't know. It's not Zoom appropriate. My bad. This is a famous function from Quake 3, I think, which is a optimized way of doing the inverse square root. And you will notice there's not a call to the square root function in this function. It's doing this big constant minus something shifted 1 to the right. Your compiler does that sometimes, is the point I was trying to make. So sometimes you'll see weird stuff. But this website I would highly recommend if you're just learning assembly or want to understand how stuff works. Things like arrays and structures get passed around in memory in a way where you're accessing offsets of those structures and stuff like that. So you do all sorts of pointer arithmetic. Thankfully, your tools can usually help you with that. So if anyone has any questions, I'll do my last call for questions, I guess. And if anyone wants to see more reverse engineering after, I can do some more of that after, but I won't waste your guys' time going through a bunch of challenges and trying to narrate what I'm doing.
This might be a dumb question, but is all assembly code the same? Like, it doesn't matter what language you type in, all is the same.
That's a good question. Yeah. So the question was, is all assembly code the same? So I think what you were trying to say is that if you are running on an x86 computer, which, like I said earlier, odds are you are, and you compile a C program and a C++ program and a Rust program and a Pascal program and a OCaml program and insert language here program, all of those compile to the same assembly code. So that's a good question. That's a good clarification. So programming languages are purely a tool for you as a software engineer or a developer. They mean nothing to the computer. All of the programming language is just a way to turn human thoughts and meaning and logic into assembly and machine code that the computer understands. That's the only language the computer understands. There's stuff like the Java virtual machine, which I won't cover today. That's a virtual machine that interprets bytecode and stuff, but that still gets run as instructions on your computer. So yeah, that's a good question. All programming languages, if they are running natively on your computer, stuff like JavaScript is an exception. That gets interpreted, but then eventually is run natively on your computer. All programming languages compile down to the same assembly instructions. And that's kind of a cool thing to explore as well. So C produces some of the cleanest looking assembly instructions. Once you start using languages like Go, I'm not dealing with that right now. Once you start using languages like Pascal, for example, Pascal produces some slightly more cursed instructions. This is AT&T syntax, which is a slightly different way of writing assembly instructions. Don't worry about that. That was a mistake. Here's Rust, for example. You'll notice that Rust inserted some extra stuff in here because Rust is all about safety, if you're not familiar. So Rust is actually, I think, checking that multiplication did not overflow. You see Swift, for example. There's all sorts of different ways of doing stuff, and all programming languages are working with the same set of processor instructions. So all code that you write in any language has to arrive at the same set of instructions, basically. But there are very different ways to do stuff. I don't program in Haskell, but I've been told that it is terrible to reverse engineer. And so far, I would agree. So yeah, that's a good question. Anyone else have any questions or back there? What do you say? We do have a CTF team. Scott would be your person to talk to about that. He is our CTF team captain. But yeah, the short summary is almost every weekend there's a CTF going on, and you can hop in the Discord and play CTF there. Or sometimes we have CTF in person, which that's a Scott question. But yes, if that sounds interesting to you, CTF is a great way to get started reverse engineering, especially more beginner-oriented CTFs. A lot of them will have reverse engineering challenges as well. Yes?
There's a Python option. What exactly is that looking at?
That's an excellent question, probably something super cursed. So you said there's a Python option. So this looks like it's being compiled to Python, what I would assume is bytecode, because these are not x86 instructions. This is probably like optimized Python bytecode or something. I don't know a lot about Python internals, but that's not, ignore that. But yeah, you can go to all sorts of stuff. Wow, that's a not so good looking one. I mean, some of this is like other functions, but yeah, Compiler Explorer is a neat website. Anybody else? Anyone on Zoom? Okay. Question from Benjamin on Zoom. Are there any tricks easy to identify when reverse engineering? Like if someone was reverse engineering Quake 3, that function I showed earlier, or the A divided by 7 example. So that is a good question. I will actually quickly, I will either embarrass myself or show a good example. But I will, so he asked about that example where the divide by 7 is optimized out weird. So that might, I wonder if that'll get optimized away, but I will see. So let's see. Oh, right, this is ARM. I don't speak ARM. I wonder if that worked or not. Is this x86? Let's go. So this one, this time it did not get optimized out. That's still there. I wonder if I pass like 03 or something, if it will. It might, at higher optimization levels, do more strange things. Okay, so here's an example. Yeah, so now it looks super cursed. That doesn't look like division by 7 at all. So in this case, this didn't get picked up, but a lot of reverse engineering tools will try to identify these things. So sometimes you don't have to know that that's actually optimized divide by 7 or something. Sometimes reverse engineering tools will see that and be like, hey, we know your antics. This is just division by 7, and it will, help you out with that. Yeah, apparently not binary ninja at this time. So I did say one of the options is that I would embarrass myself. So it seems like that was the case. I don't think, I do know that there are scenarios where that does get applied, and it might depend on the architecture too. But I have no more questions from Zoom. If nobody else has any questions in person, then I think we're done here.